Let me.
So our next talk is by Harald Helfgott from the University of Göttingen. He will give us a presentation on expansion, divisibility, and parity. So go ahead.
Well, thank you very much, Florian. All right, so that's a tough act to follow. I will be talking about a recent preprint of mine with Max Radziwiłł. So I will start with the number theoretical motivation. A result is really a result on the properties of a number theoretical graph and how that graph is an expander in a strong sense. And that has all sorts of consequences. But I thought it would be interesting to start with what was at least my original motivation, namely to improve a very nice result from tau from a few years back in several ways. All right, but let us start with why this sort of problem is interesting. So take lambda. Lambda, let it be the Liouville function. So it's -1 to the number of prime factors of n counted with multiplicity. That's lambda of n. Then that the average of lambda is little o of 1, that's equivalent to the prime number theorem. And that the autocorrelation, if you wish, of lambda with itself is going to 0, that's open and very, very hard. That's what's called Chaule's conjecture in degree 2. Chaule's conjecture in degree 1 would be what I wrote just above. And it's considered to be about as hard as, say, twin primes or what have you. You know, that may be a matter for debate now. At any rate, some years ago, in 2015, Matamaki and Radziwiłł proved something astounding, that so for any h going to infinity, as n goes to infinity, lambda of n averages to 0 over most intervals. Well, by most, I mean going to 100%, most intervals of length h within, say, n and 2n. Can you hear me?
Sure.
Yes.
Okay, very good.
Yes, thank you.
Yes, very good. So before this was known for h bigger than, say, n to the 1/6, I think was the record, but it wasn't known for h equal to n to the epsilon, and it certainly wasn't known for h arbitrarily small. H could be log n, and this would still work. Now tau, using Matamaki and Radziwiłł, proved what he calls weak or logarithmic Chaulle in degree 2. Namely that if he has this self-correlation, right, but he has his weight 1 over n, and accordingly he divides by log x rather than by x, then this goes to 0 as n goes to infinity. All right, so part of the challenge was to improve, well, not just the bound in tau, as I will say in a moment. The bound in tau has actually a quadruple log. I also wanted to do something that I felt was the natural road. Now, given that motivation, let us go to the more abstract level that I wanted to start with originally. Oh my, what's this green screen? I don't know what's going on here. Oh, this is very upsetting. Okay, hopefully this will disappear forever. Okay, I have no idea what's going on here. One moment, please. I apologize. My laptop died on me a couple of days ago, and I'm using a very old laptop that I was using before as a TV for the cat. One moment. Okay, maybe this will. Yes. Okay, this is better. All right. So, very good. I will define a graph that has as its vertices the set of integers. From now on, it will be called bold n, between n plus 1 and 2n. And I will take a set of primes. Part of the point is that I want to examine a pretty arbitrary set of primes. a set of primes, not too large, but not necessarily very small. And I will draw edges between n and n plus p, two elements of bold n, p an element of bold p, if p divides n. So that my graph is very simple. So an edge looks like this. I'm going to draw an edge between n and n plus p, a non-directed edge. It goes both ways, if and only if p divides n. All right. And then here, my text has disappeared. So this graph has, in essence, already been considered. This was a graph equivalent to this one was discussed in Matomaki, Rajiv al. Where they proved that it's locally connected almost everywhere. And Tao also discusses, I mean, if you know how to read it correctly, that in his own paper, I had a quote from Tao here that has mysteriously disappeared, but it says that it may be possible, I quote Tao, to estimate expressions like this one over here by establishing some sort of expander graph property for what is equivalent to this graph here. It's the graph gamma. Unfortunately, he says, he was unable to establish such an expansion property as the standard methods of establishing expansion do not work. Well, we will later see that the first step of a very traditional strategy does work. But let us define a few more terms first. So there's a linear operator called add or adjacency operator, which is defined as follows. It's an operator on functions on the vertices, say complex values functions on the vertices. And what is this operator? Basically, it replaces your value by the sums of the values of your neighbors. So the value of this new function, add of f, at v, is just going to be the sum of f of w for all v connected to v by an edge. All right, and we define the inner product as you might expect, just this way. And it's actually quite easy to show. Well, I'm sure it was easy for Tao, but it's actually not hard to show that translating things into this language expresses them a bit differently, but it's exactly this, that if you prove that the inner product of lambda with add of lambda is little of L for some p, where little l is the sum of the reciprocals of the primes in p, then Tao's result holds. Okay. All right, well, what now?
What is lambda?
Lambda is a Liouville function. What on earth is going on? I'm very sorry. I'm having some technical difficulty. It has. Let me see. Oh, now it's working. Okay. Let me share this other screen. Okay, one moment, please. Tap. Okay, this is what I meant to share, and here you see the quote by Tao, and you don't see what I just wrote, but let us ignore that and go to the next page. Very good. All right, so now let's take a step back. I remind people that an expander graph is a regular graph of degree D, that is a graph such that a graph for which the degree of every vertex is D, in which the eigenvalue, every eigenvalue lambda other than the obvious eigenvalue D, which is the one that corresponds to constant eigenfunctions. If everybody has the same value, then it's clear that taking the adjacency operator is just going to multiply that function, that constant function, by the number of neighbors D that every vertex has. But other than that one, if you consider any other eigenvector, you're going to have that the eigenvalue is at most 1 minus epsilon times D in absolute value. So we can ask ourselves, so is our graph gamma in fact an expander graph? Well, that's too much to ask and also too little to ask. It's too much to ask because gamma is very local, meaning that the primes in P, even though we will not just be considering very tiny primes like tau has to because of his method, they will be small compared to n. And because of that, the edges are small compared to n. And why does that mean that the graph cannot be an expander? Well, one quick way to see it is that in expanders, random walks equidistribute quickly. Whereas in this graph, because the edges are short, you cannot get that far away from where you started in a small number of steps. On the other hand, it's also too little to ask, but rather what we want is some form of strong expansion. Why? Because what we actually want is lambda as gamma lambda to be little o of L. L here is the average degree of gamma. It's not a regular graph, so another reason why it could not literally be an expander graph. Not just, but that doesn't mean that we are asking for too much, because after all, there are Ramanujan graphs, and more about that later, where the eigenvalues, the non-trivial eigenvalues are all smaller than 2 times square root of the degree, which is L. And if L goes to infinity, as it will have to for the proof to work, and for the statement to make any sense, then that would be fine. So we are really asking for some sort of strong local expansion almost everywhere. Okay, so how do you define? So before we prove what we want to prove, we have to define what we want to prove. And this is actually not so trivial, because one way to see it is to say, well, instead of having just a constant eigenfunction to take out, we should take out all things that are locally almost constant. But it's hard to, I mean, that's a concept with a gray area. How constant is something that is locally almost constant? It's true that it means that we are on the right track, because after all, what Matomaki and Radziwiłł proved is that lambda is orthogonal to locally almost constant functions. But still, well, one good way in retrospect to go about it is to define first a naive model for our graph gamma, where we always join n and n plus p, but we assign to it, so no conditions of divisibility here, we assign to it the weight 1 over p. All right, and now we define the operator add gamma minus add gamma prime. Well, yeah. So Matomaki and Radziwiłł, and this is really how we get to use Matomaki and Radziwiłł, or rather a simple variant thereof, which is already present in their paper, one of their papers with tau. So the result implies that gamma, lambda comma add of this naive model is small. So just using this as a black box. So if we prove that all eigenvalues of A, after all, we have basically killed the constant functions and locally constant functions by taking out the naive model. If are small, this will show that obviously. And so using this fact, we will have got that lambda add gamma, lambda is small, which proves weak Chowla in degree 2, reproves it, hopefully with a better bound. All right, this can be quite true. Not least, and here the fact that the graph is not regular matters. It cannot be quite true because there are vertices of high degree. Very high degree, not very many of them, but higher, say, than L squared, and in fact, much higher than that. And that automatically means that this statement cannot be true as stated. However, so we will work with some restriction A to some X, where X is a large subset, so the complement is small. No, and by this we just mean that we define it as follows. So Ax applied to a function is just going to be, we first restrict f to x, we then apply a, and then we restrict to x. All right, that's needed. And that still gives us what we want, basically because lambda is bounded. But in fact, it's, it will be a stronger result. It will have other implications, as we will see. Okay, so now we come to the main theorem. So let NP the graph and A and L be as above. And we assume, so Tao proved that what he wanted to prove by showing that there exists a set of primes P for which this is true. Sets of primes that are, by the way, very small indeed. All of these primes are smaller than log n, and that puts some restrictions on the applications, besides making the bounds have lots of logs. That's one of the reasons. So he shows that there is a P for which this is true, and he uses that using entropy-based arguments. We want to show that basically every P with some very soft conditions, well, what soft conditions? Yes, that it's contained in some interval h. Here, h is at most log h is at most log n divided by L, and log h0 is greater than log h to the 2/3 plus epsilon. These are the conditions on the interval. Other than that, we are fine as long as, well, we also don't want L so small, but then there exists an X that is large, its complement is small. Such that every eigenvalue of A restricted to X is indeed little o of O. In fact, it's O of square root of L. So as long as L goes to infinity, which it has to for things to make sense, we are fine. In fact, this is basically O of Ramanujan. So up to a constant factor, it is optimal. All right. Now we have, as an immediate consequence, we have the following. I will not disappoint. Let me state, I have 1 minute left, so let me state first the corollary that improves on Tao's result. Yes, so for any W, and it could be X, say.
Harold, you started 10 minutes late, so you can take another 5 minutes.
Oh, thank you very much. In fact, let me just, okay. So in particular, this covers the case X, the case W equals X. So this will be O of 1 over log W. Let me just simplify matters, since to be fair, since Tau also has a variant with W. Okay. No, so for comparison, here Tau had, well, he found it's not explicit, but it can be made explicit. That's in a paper in Spanish by Adrian Ubis and myself. So he can do log 1 over log 4 logs alpha. So we got 1/5 Ubis and myself, but it's just an expository paper. I'm sure one can do better. And Tau and Teravainen managed to do better. They managed to get, well, they also don't do it explicit, but their method gives 3 logs. Yeah. In order to do better than 2 logs, in order to get 1 log, you would need to define a different graph. You would need to work with edges that are not primes, but generally composite numbers. Whether that's possible or not, that's that's the next step, but it's not this paper. But let's proceed. So Tau and Teravainen also showed Tau and Teravainen also showed that genuine Chaula is true at most scales. And I will not state this precisely. I will just say that, again, we go from a triple log to the triple log bound to a double log bound. All right. But there are also ways in which one can get, I mean, the bound is qualitatively strong enough, and it's general enough that it can be applied to get results that seem to be qualitatively stronger. So, for instance, we can also get, say, that take K to be a popular number of prime divisors to have. Something that is not way out in the tail of the distribution. Now let skn be the set of integers in n having exactly k prime factors. Omega means counted with multiplicity. Not that that matters. Then the average of lambda of n plus 1 over sk comma n is little o of 1. So we are just averaging lambda of n plus 1 over integers n that have a given precise number of prime factors. Yeah. Unfortunately, we cannot do it for primes, that is for numbers with 1 prime factor, because 1 is not a popular k to have. It's not in this range, and the results are just not quantitatively quite strong enough. Maybe if one, probably if one managed to show it for the graph with composite edges, one would just fall short of that classic conjecture. No, who knows? Perhaps if one improves it a little. At any rate, it seems I have -3. Okay, how many minutes do I have left? 2?
Sure, yeah, you can take 2 more minutes.
Let me just say very briefly. So the first step is actually the oldest thing in the book. It's probably in some Babylonian tablet somewhere. So sketch of proof. So yeah, so if we show that the trace of ax to some higher power to k is small, and we also showed, and this is not hard, though some people seem to be surprised, that one large eigenvalue implies that there are many. So it's the old high multiplicity argument, but not quite, because it's not that an eigenvalue has large multiplicity. It's more that one large eigenvalue implies many large eigenvalues. And that, I repeat, is not the main point. People seem to be impressed by this. It's really easy. Okay, if you show this, then you get the expansion statements. Yeah. Okay, so it's all about studying this, but this is a sum. Again, ancient Babylonian insight. This is a sum over closed walks of, yeah, this is the product of edge weights of length to k. So and closed walks, I mean in the graph, and if you wish, the subtraction of the two graphs, namely the weight of the edges gets subtracted. And so this becomes very quickly a problem in combinatorial analytic number theory, if you wish. And you have to distinguish between 3 kinds of walks. So walks where there are repeated, there are some enough non-repeated primes and in this case, you're going to get a lot of cancellation. And this is a part that entails a lot of technical difficulties because we had to restrict to a set X. Otherwise, it would be extremely simple. One non-repeated prime would be enough to get total cancellation just by the Chinese remainder theorem. But if you wish, this is what tells it. Having cancellation tells you that the naive graph, a random walk on the naive graph is a good model for the random walk on gamma. So that you expect to have the same limiting, you expect the random walk on gamma to have the same limiting distribution as a random walk on gamma prime, no, which is really what you are aiming for. And then you have some walks that you hope to show are rare, and that's actually subtle. So for instance, there are the walks that are trivial in the sense that a word is trivial. It's where you're basically dancing on some sort of tree, no? You go like this, and then you dance back, and then, yeah, and you go back. That's one example. But even those, showing that they are rare, I mean, there are not so many trees. The number of, the Catalan number grows only exponentially, but showing that you don't have funny things because of the labeling, that's subtle. Subtle enough that we didn't realize it at first. And then you have the case where you are not in a rare, you don't have one of these walks that you don't like so much, and where you have not so many non-repeated primes. And then what you are aiming is to show that there are many independent conditions of the following sort. Well, what sort? If you have a repeated prime, if pi is equal to pi prime, and you have that pi divides n plus sigma 1 p1 up to, which is what you need to have if this is going to be a valid step in gamma as opposed to gamma prime. And you also have that pi, which equals pi prime, divides n plus sigma 1 p1 plus. Yeah, so clearly you are going to have that pi divides the difference, which is just sigma I pi up to sigma I prime minus 1 pi prime minus 1. Yeah, so you need to have many independent conditions. Well, so if you have one such condition, it's clear that you are going to win a factor of H0, but that's not enough. You need to use many such conditions in order to win. And then, of course, you have to make sure that you know what you mean by independent. You use a bit of geometry of numbers. It turns out to be a rank, and then you have to produce. You get very many of these divisibility conditions, but it's the tricky part is to show that you can choose your dividing primes if you wish, and your dividend primes if you wish, so that you end up with a high degree of linear independence. And that, I would say, is the basic trichotomy that lies at the heart of the proof. Though I would really say that the heart of the proof is this and that. Though really, when you really get to see, multiple contour integrals and the like only for number one. So I'm sure some people will say, oh, the rest is just combinatorial analytic numbers here. Okay, I think I can finish here.
Thank you very much.